1155. Number of dice rolls with target sum. All right, so let's go ahead and get right into it so I don't start rambling about some random unrelated topic. You have n dice, okay? And each dice has k faces numbered from 1 to k. All right? Given three integers, n, number of dice, k, the number of values that can be on a dice, and target, return the number of possible ways out of k to the n total ways to roll the dice so that the sum of the face-up numbers equals target. Since this answer may be too large, return it modulo 10 to the 9 plus 7. Okay, so the idea is like, you have a set of dice, right? You could think of like a standard, 6-face dice. You roll all the dice and you count the sum of the numbers that you roll, and that sum, how many ways can that sum equal target, right? Um, so if we look at this example, right, if n equals 1, target equals 3, k equals 6, so it's a 6-face die, right? There's only one way, right? Because you roll a 3 or you don't, right? And there's only 1 out of 6 ways that you can roll a 3, so there's one way that you roll a 3, right? You roll it once, you could get a 1, you could get a 2, you could get a 3, you could get a 4, you could get a 5, you could get a 6. So since the target is 3, there's only one way that you could do that, right? And another way you can think of that is like, well, if I roll this dice, right? I roll this dice, I get a 1. This is the answer, right? If I roll this dice and I get a 2, it's not the answer. If I roll the dice and I get a 3, the target is 3. Sorry. This is the answer. 4, 5, and 6. Right, so this is the only way to roll the dice once and get the target of 3. All right. And since there's only one dice, right, these are the only outcomes. So you can kind of think of this as being a state, right? So just trying to find a way to model this so it makes a little bit more sense. Okay, how about 2 and the target equals 7? Well, I start off this match, right? And how many ways can I, if I just enumerate all the possibilities, right? So I roll a 1 first. Could roll a 2 first. Could roll a 3 first. Could roll a 4 first. Could roll a 5 first. Or I could roll a 6 first. Now, since there's 2 dice, right, I can't determine what the answer is just from this information here, right? So I have to roll another die, right? But the thing is, from this state, I can roll any 1 through 6 again, right? So this problem kind of grows exponentially a little bit. So that's why this is kind of difficult, right? Because from here I can roll a 1, could roll a 2, could roll a 3, right? A 4. Same thing here, right? There's 6 coming out of each of these too, right? Because there's 6 things that I can roll, right? Because I can roll this first dice, then I can roll the second dice, right? So for any first dice, there's no relationship, right? If I roll a 1, it's just as likely that my next roll is 1 through 6. And then at the end, I should just enumerate the number of ways that I can get to the target, right? So like here with the 1, I'd roll a 1 and then 1 with a 5 or a 6, right? 1 with a 6, that would get me to, oh wow, there's a big delay. I just realized that right now. So if I roll a 1 with a 6, right, that's how I could get to 7. I could roll a 2 with a 5, a 3 with a 4, a 4 with a 3, right? And that gives you 6 possible. 5 with 1, 5 with 2, 6 with 1. And then you'll notice that, yeah, this problem it grows really fast, right? Because if you look at the system, there's kind of like this exponential nature to it, right? So it's going to keep expanding out. So one thing to notice, I guess, is that these constraints are very small, right? It's n and k are less than 30, targets less than 1,000. So if I had a linear algorithm in terms of, not linear, but like product of nk and target, that would be 30 times 30, so 10 times 10 times 900, 900 times 1,000, 900,000. So this would be less than 1,000,000 operations, right? If I could have some sort of linear algorithm that utilizes all of these variables together. So I'm not too worried about like trying to find some algorithm that doesn't depend on like all three of these, or some algorithm that's linear with respect to all three of these, right? Because these constraints are so small that indicates that there's probably a kind of the optimal algorithm for this problem may not be that efficient. So again, maybe always looking at your constraints can indicate good things. So one way you can think about this problem is, well, since we don't need to know like the values that get us to a solution, we just need to know the number of ways that can get you to a solution, right? So if you're looking at target, right, we're trying to find the number of ways that can get us to this target value. So we'll just call this target value target, I guess, right? Now, in order to get to target, all right, there's a huge delay, so I'm going to unplug and replug in, and hopefully that resolves it. No promises, though. Right, if I'm trying to get to some target value, how can I get there? So try to think kind of backwards about how this is going to work, right? So if we think of our target value, this delay, dude, so frustrating. Apple products can be so bad sometimes. Like, it's crazy how bad they can be. Just buggy for no reason. Okay. Okay, that's better, I guess. No, it's not. All right, whatever. There's going to be a significant delay, and there's really nothing I can do about it. Okay. So the only way you can get to some target value is on the nth roll. So if we think about the nth roll, right? So we have this nth roll where we're going to roll and get to the value of target. Well, what would that require? Well, there's k dice that I can roll to get here, right? So there's this kth dice, this k minus 1, right? And there's the 1 die, right? So these are the previous rolls that I can roll to get to target, right? So I could roll a 1 and get here. I could roll a k minus 1. So there's previous states, right? There's previous rolls that I could roll to get to target. But what would the value of each of these have to be? Well, in order for me to roll and then just assume that there's, this whole other system here, right, that leads into these systems here. So what would the value have to be here in order for me to roll a k and get to target? Well, the value here would have to be target minus k. Here would have to be target minus k minus 1, target minus 1, right? If the value, like if I enumerated all of the rolls so far here, and the value of all my rolls together was target minus 1, if I roll a 1, then I'll get to target, right? If I do all my rolls and I get to here, and my sum of all the rolls that I've done so far is target minus k, then only by rolling k will I get to target, right? So to get to any state, right, to get to any value, the number of ways to get to that value, right? So the number of ways to get to some value is the sum, or let's think of it like this. So if we had a dynamic programming system like this, right? So this is the number of ways to get to a value using the nth roll, right? So the number of ways to get to target right? The number of ways to get to target with the nth roll is the sum of the number of ways to get to this node plus 1, right? And this node, because it's k minus 1 and k and so on and so forth. So the number of ways to get to a value using the nth roll. So if we say d of a value v for the nth roll is the sum of the ways, we'll do it in a standard math notation, right? For each value, we'll call it a roll value, r equals 1 to k, okay? Because you have k rolls. The number of ways to get to v minus k with the previous roll. Right? So this is a recurrence relationship about how this data works. What this is essentially saying is the number of ways I can get to a value, right? The number of ways I can get to target on the nth roll is the number of ways that I could get to each of the values that can lead to target, right? So the number of ways I can get to v, oh, I put r, k here, it should be r, sorry. Right, the number of ways I can get to some value v on the nth roll is rolling the dice. So either I rolled the dice and I got to v minus r on the previous roll. How many ways can I do that? Does that make sense? Right, the idea is like, say this was, how many ways can I get to 7 on the second roll? Right, so what I could say is, how many ways could I get to 7 on the second roll is the same as the sum of, so if we look at this example here, the sum of r equals 1, 6, d of v minus r on, so this is 7, on the first roll. 7 minus r, right? So it's saying the number of ways I can get to my target of 7 on the second roll is the same as the sum of the number of ways that I can get to 7 minus r on the first roll for each r value that I can roll, right? So this is basically saying d of 7, 2 equals d of 7 minus 1 on the first roll plus d of 7 minus 2 on the second roll plus d of 7 minus 3 on the first roll plus d of 7 minus 4 on the first roll plus, I'm just going to enumerate through all of them, 7 minus 5 on the first roll plus d of 7 minus 6 on the first roll. So I'm basically saying here's the number of ways I can get to 7 on the second roll is the same as the number of ways I can get to 6 on the first roll, because what I'm building in here is saying, okay, 7 minus 1 is 6, so that's basically saying if my second roll was a 1, then my first roll, how many ways can I get to 6 on the first roll, which would be a 6 here. Right, so I roll a 6 and I roll a 1, and that's how many ways can I roll a 6 and roll a 1? That's just 1, because we're talking about the base case here. 7 minus 2, that's basically saying, well, how many ways can I roll a 2 on this roll and get to 5? Well, since it's just 2 dice, there's just a 5 here, right? How many ways can I get to 4 and 3 using a 3? How many ways, if I rolled a 4, right, that's what this is basically saying here. If I rolled a 2, if I rolled a 4, if I rolled a 6, if I rolled a 5 on my nth roll, what's the state of the previous roll? So how many ways can I get to 3 where I just rolled a 4? How many ways can I get to 2 if I just rolled a 5? How many ways can I get to 6 if I just rolled a 1? Right, and you'll see here that there's 2, 4, 6 possible ways, which is the solution here. Right, now this is just the base case because there's only one way to do each of these things, right? There's only one way to make all of these things happen, right? There's only one way to roll a 6. There's only one way. With one roll, there's only one way to roll a 6. With one roll, there's only one way to roll a 5. right? With one roll, there's only one way to roll a 3, right? But you could imagine this expanding out, right? So if you said like, how many ways can I roll to 8 on my third roll? Well, that's just the sum of r equals 1 to k, which is 7 in this or 6 in this example. Sorry. This is a value 6 of d of, well, how many ways can I roll to 8 minus r on my second roll? So there's other values we would need to calculate here, but for one of these values, it would be, you know, if we rolled a 1, that would mean that we have d of 8 minus, so there's other things that are getting summed here, right? I'm just saying that this is one of them. D of 8 minus 1 on the second roll, which is 7. So we know from here, okay, d of 7, 2, that's 6, right? There's 6 ways, there's 6 possible things that I could roll, and adding 1 will get me to 8, right? So if I roll a 1, there's 6 other combinations of things that I could roll such that it equals 7, and then I could get 8 by adding in this additional 1, right? So there's a set here of length 6, and there's all these values. In particular, there's this roll and this roll, right? There's all of these rolls, 6, 1, 2, 5, 4, 3, 3, 4, 6, 1, and I could attach a 1 as my third roll to all of these, right? That's essentially what this is saying. I can attach a 1, right? I can attach a 1 here. I can attach a 1 to this one, a 1 to this one, and so on and so forth. Okay, so that's the recurrence relationship of this system. Now, since the roll is only based on the previous roll, we don't actually need to remember, like, we don't need to remember information other than information from the previous roll, right? Since d of 3, like, for generic values, right, for n, right, the value for roll n is only dependent on roll n minus 1. So we don't need to keep information about roll n minus 2 or roll n minus 3. So this is just going to constrain our space to give us better space complexity. But the idea is you don't need to base your information off rolls that are far in the past because they don't contribute to the current roll state, right? In order to get to target using k rolls, you just need to know information about n minus 1 roll. Okay. So with that, let's go ahead and get started. So we'll create this D array. So 1. So the only roll values you need to consider is 0 through target, right? Because you'll never rolling anything over target, like every time you roll the dice, the value can only get bigger, right? So since the value can only get bigger, you're never going to need to consider rolls values. Like if you sum up the roll values and they're greater than target, you just avoid them because they're not going to help you, right? You're never going to get the value lower since you can never roll a negative die. So we don't need to consider values greater than that. And then what we'll do, don't forget the mod. So this is just the modulo that we're going to use in the system. So we're going to look at each roll, right? So we're going to roll in range n, right? Because there's n rolls. Right? There's n rolls. Okay, there's n rolls. And then we'll look at each value in the range, right? So each roll value v in range, well, you can't roll a 0, right? So you can roll a 1, and you can roll all the way up to target, right? So we go target plus 1 because that won't include target plus 1, so it'll include target. And then the number of ways you can get to that value, right? The number of ways you can get to target is the number of ways you can get to target minus 1, target minus n plus 1, minus target plus target minus k. Right? So we can look at each roll value, I'll call it T, I guess, in range. So you can roll a 1 all the way up to K. But if k is larger than target, right? Because maybe the value you want is 3. You don't want to have negative values that you're considering. So we'll just say min of k and target plus 1. Right? Because you don't want to roll. Does that make sense? Because like if target was 4 and k was 7, you don't need to consider values of k that are greater than target, because that'll never get you the answer, right? Like if my target, for example here, right? If my target is 3 and k is 6, I don't need to consider the dice values of 4, 5, and 6, right? Because it's never going to give me the target. So I only need to consider k equals 3. Okay, so then d at value plus equal the number of ways sorry, I'm trying to think about, okay, so I'm just doing the recurrence relationship. So v minus the value minus t. So we actually call this r, right, in the system, so we'll call it r here, right? Remember here we called this thing r, right? V minus r. So I'm doing the r values from 1 to k, but it's really the min of this in k, and then it's d of v equals v minus r n minus 1 on the previous state. So here's this, and then I'm going to mod it by mod so I don't forget. And at the end, we're just return d of -1 mod. Okay. But, okay. So we need to have the state, and then the state be updated after the complete iteration for each roll. So we'll have a new d for each thing times target plus 1. And then we'll just update new d like this. And then at the end of the loop, we'll say d equals a new d. That way we can just have an array. We figure out all the rolls for the next roll given the previous roll. And then we say, okay, now d is this previous roll. Right, so that's the idea there. Okay, let's go ahead and submit that. What did I do wrong? So it's overestimating the value. Someone here screaming at me like, you don't see it. So you look at each roll. This is saying how many ways can you roll to 3 no, how many ways with 3 dice, with the dice up to 18, can you roll to 10? Okay. What am I doing wrong? I don't get it. There's something in here. I have n rolls. For each roll, I'm going to go from 1 to target. plus 1. I'm going to go from 1 to the min of k. All right, so I'm going to print D here after each roll just to give me a little debugging help because I'm not exactly sure, well, not exactly sure what I'm doing wrong here. So hopefully it'll appear to me. Okay. So yeah, there's one way to do both of these things. Okay, so this should not be 9, right? Because the number of ways to get to 1 would still be 1, right? Because you could only add in, or no, there should be 0 here. So something's going negative. So v minus r, yeah, so this is negative. So for any value, I'm pretty sure that's what it was. Okay, cool. Yeah, so for any value, right, like if the value is 5, then I'm trying to say how many ways can I sum up to 5, then my previous roll has to be less than or equal to 5, right? So if the current value, I'm saying how many ways can I roll up to 12, right? Well, then how many ways can I roll up to 3? Okay, let's say that. If value is 3, so how many ways can I get the value of 3? Well, that would mean that all my previous rolls to get up to 3 have to be at least, can be at most 3, right? The number of ways I can get to this value of 3, well, then all my previous rolls, my previous roll could be a 1, my previous roll could be a 2, my previous roll could be 3. My previous roll can't be greater than 3, which is why this was not working, because it was going negative and it was pulling values that you couldn't get, right? So basically when Python has a negative value, when this was negative, it would go negative in the array. Going negative in the array means that it would pull in values from the back of the array. So that's just the way that Python works. It just wraps around when you go negative. So it was adding in additional counts that don't actually exist. So that's why it was overcounting. Okay. So, what I had here was the min of k and target. So k definitely has to be less than target, but even more than that, it has to be less than the current value that you're looking at. All right, so what's the run in space complexity of this? The time in space complexity? All right, so if we have to look at each roll, so I'm just going to treat these variables as they are, n, k, and t. Right, so for time, I have to look at each n rolls, right? Then for each n rolls, I have to create this new array of size target. And then another, I have to loop through target. And then I have to loop through values from 1 to k. So that's, for each roll, I have to do target operations. And then I have to do at most k operations for each target to see, for each value, I have to do n rolls. For each roll, I have to look at values from the range of 1 to target. For each value from ranges of 1 to target, I have to look at most k roll values that can lead you to that value for each target, for each n, right? So that's O of big O of n times target times k. Okay. And then for space, well, we create D, which is of size target. And then since we kind of were, we were kind of not intelligent, but right, since we considered the fact that we only needed information from the previous roll, we were able to create something that was only a size target, and that's the only thing you update here, right? So this is a constant, but this scales with the size of target, so the big O of target. And that's it, folks. Sorry about the bugs. Sorry if my solution was a little confusing. I've been kind of off my game lately. Peace.